Okay, I'm going for the pH, pOH, and the hydronium hydroxide ion concentration problems. Number one, if pH is 11.2, what is pOH? Well, the formula for this is pretty simple. 14 minus pH equals pOH. 14 minus 11.2 gives us 2.8. And that is my pH. Number two, if hydronium ion concentration is 0.00002210, what is pH? Okay, so for this one, pH equals negative log of the hydronium ion concentration. So negative log of 0.0000212210. Plug it into the calculator. Negative log 0.00002210, close parentheses. And I'm looking at 4 sig figs here. Remember that 0 counts. So I'll call this 4.656. Number 3. If hydroxide ion concentration is 0.0124, what is pH? Two ways you can go about this. You can go hydroxide ion concentration to hydronium ion concentration to pH, or what I'm going to do is go OH minus concentration to pOH to pH. So to find my pOH, negative log of OH minus, that's going to give me pOH, so negative log of 0.0124. Negative log 0.0124. So pOH equals 1.9. Let me check my sig figs. 3 sig figs. 1.91. pH equals 14 minus this, so it's going to be 12.09. Yep. And you might think, well, wait, how do you have 4 sig figs here? Well, really, this is based on sig figs. This is based not on sig figs, but on the subtraction rules. When I do 14, and we assume that that 14 is like infinite sig figs. So 14 minus this, I'm going to use the same number of decimal places. Number 4. Okay, if H3O plus equals 3.25 times 10 to the negative 5th, what is hydroxide concentration? Formula for this, H3O plus times OH minus equals 1.0 times 10 to the negative 14th. So if I know this and I'm looking for this, we're going to say 1.0 times 10 to the negative 14th divided by hydroxide ion concentration, which in this case is 3.25 times 10 to the negative 5th. That equals my OH minus concentration. But this is all about carefully plugging it into the calculator. I'm going to enter 1. I like to use the E. I think it works very well. I can say 1E negative 14 equals. So that value is now stored. Then I'm going to say divided by, I'm going to put this in parentheses, 3.25 E negative 5, close parentheses, gives me 3.08 times 10 to the negative 10th, and that is my hydroxide concentration. Number 5, if H3O plus equals 5.21 times 10 to the negative 8th, what's pOH? Again, there's 2 steps you can do. What I'm going to do is turn H3O plus into pH, then turn pH into pOH. Because pH to pOH is very simple. You just use that 14. So to find my pH from this, I'm going to say pH equals negative log of the concentration of hydronium. So for this case, negative log of 5.21 E negative 8. 7.28. So therefore pOH is 14 minus this. pOH equals 6.72. That's number 5. Okay, we're now going to complete this table at the bottom. So for the first one, we have H3O plus is 0.250. Looking for OH minus. So to find OH minus, formula we use is 1.0 times 10 to the negative 14th divided by this gives us OH minus concentration. So let's find that out. 1e negative 14 equals, divided by 0.250, that's going to just be times 4. So concentration of OH minus equals 4 times 10 to the negative 14th. pH, pOH. For this, we're going to say it's negative log of this gives me pH. 0.602. Negative log of this gives me pOH, 4e negative 14. Okay, so negative log of that, 13 point, and I'll go with 3 sig figs here, 0.4. Another way you could figure this out, once you get that, just do minus 14. So you can see it's pretty close. Next one, we are given OH minus as, oh, forgot, is this acidic, basic, or neutral? Easiest way, look at the pH. If it's less than 7, it's acidic. So this is definitely acidic. Okay, 5.25 times 10 to the negative 3rd is my OH minus concentration. So for this, I'm going to say 1.0 times 10 to the negative 14th divided by that will give me the concentration. 1e negative 14 divided by parentheses 5.25 e negative 3. If you don't do the parentheses, what the calculator thinks you want to do is divide it by 5.25 and then multiply what you got by this. Often gives you the wrong answer. 1.90 times 10 to the negative 12. By the way, these numbers should be about negative 15, and that's because usually the front numbers are going to multiply together to get 10. So like 1.9 times 5.25, that's going to give you 10. So you're going to end up with 10 times 10 to the negative 15th, which really is 1 times 10 to the negative 14th. So you might think, wait, shouldn't these equal 14? No, they should actually equal negative 15. Unless you have like 1 and 1 in front. Okay, pH, so negative log of this. Negative log of that gives me 11.7, 3 sig figs. And pOH, I can just subtract from 14. Or I could do negative log of that, 2.3. And this one is definitely basic. This is more than 7, so it is basic. Next one, I tell you the pH is 6.121. Okay, so let's get our pOH quickly. 14 minus this, 7.79. Okay. For these, my formula now is going to be 10 to the negative pH gives me this, 10 to the negative pOH gives me this. 10 to the negative 6.21 gives me 6.17 times 10 to the negative 7th. For this, 10 to the negative 7.79 gives me 1.62 times 10 to the negative 8th. And is this acidic or basic? pH is less than 7, acidic. Last one, pOH, 4.31. So therefore this is 14 minus that, so that's going to be 9.69. Alright, let me just double check my math. Yep. I'll do this one next. So 10 to the negative pOH, 4.90 times 10 to the negative 5th. And my H3O plus concentration, 10 to the negative 9.69 gives me 2.04 times 10 to the negative 10th. So again, negative 10, negative 5 adds negative 15, but this together would give you 10 times 10 to the negative 15th, which is 1 times 10 to the negative 14th. Okay, on to the back. Dissociation equation for hydroiodic acid in water. Hi plus H2O. So whenever we deal with acids dissociating, include the water reaction because that's kind of the whole basis of acid-base reactions. So since this is strong monoprotic, it's all in one step. So this is going to lose its H plus, becoming I minus, aqueous. And let's write our states here. All acids are always aqueous. And this H plus is going to go onto the water, forming H3O plus aqueous. So that's my dissociation reaction. Number 7, phosphoric acid, H3PO4 aqueous plus H2O liquid. So now we have a triprotic acid, 3 protons, so this is going to happen in 3 steps, 1 proton at a time. So first it's going to lose 1 proton to a water, forming H2PO4 minus aqueous plus H3O plus aqueous. Next, this product is going to lose a second proton, so I'll rewrite it down here, H2PO4 minus aqueous plus another water liquid yields. So after this loses a proton, it becomes HPO4 2 minus aqueous plus a second hydronium. This is now going to lose its third proton in another step. HPO4 2 minus aqueous plus H2O liquid yields PO4 3 minus aqueous plus H3O plus aqueous. So really what ends up happening is this is going to turn into just the polyatomic ion, anion, plus 3 hydroniums. Because remember, if I just ask you what this splits up into directly, it's going to be 3 hydrogen atoms, or hydrogen ions, and 1 phosphate ion. Well, those hydrogen ions, they don't just float there randomly in water, they're going to find water. So we get 3 hydroniums and 1 phosphate. Number 8. What's the pH of a 1.25 molar solution of nitric acid, which is a strong acid? Well, for a strong acid like HNO3 aqueous, because it's monoprotic, I know it's 1 to 1. So if I have 1.25 molar of this is going to break 100%. This H is going to leave, H plus, find a water, stick onto it, and form H3O plus. So if the concentration of that is 1.25, my hydronium ion concentration is also going to be 1.25 molar. Number 9. What is the pOH of a 0.0200 molar solution of sulfuric acid? So another strong acid, but this one is diprotic. So H2SO4. This is going to produce 2 hydronium ions for every one of these. If I were to draw the equation out, it would be basically this turns into HSO4 minus, and then HSO4 minus turns into SO4 2 minus. So because this creates 2 hydronium ions, you need to basically double the concentration to find how many hydronium ions you're going to get. 0.0200 molar. So therefore my H3O plus concentration is going to be 0.0400 molar. Okay? I just realized in number 8 we forgot to actually find pH. Well, if that's my concentration, negative log of this is negative 0.0969. And that's not a typo, this is actually a negative pH. For very concentrated strong acids, you can get a negative pH. Okay, in this example, we've doubled the concentration to get our hydronium. We're looking for pOH though, so to do this we need two steps. I'm going to find pH, then pOH. Negative log of 0.0400 gives me 1.40. Therefore, pOH is 14 minus this, 12.60. Last problem. What's the pH of a 0.500 molar solution of iron 3 hydroxide? Assume this is a strong base, 100% dissociation. This is actually like a not sure if it would be called a tri-basic formula, but basically it's FeOH3. So if this fully dissociates, it's going to break down into one iron, which is iron 3, and 3 hydroxides. So again, for every one of these, we get 3 hydroxides. So if my concentration of this is 0.500, then my concentration of OH minus, I can just draw it down here, is going to be 1.50. Because for every one of these, I get 3 of these. So this tells me my OH minus concentration equals 1.50. I'm looking for pH. Well, let's find pOH from this. pOH equals negative log of this. So I can tell we're going to get another negative answer. Yep, negative 0.176. Again, pOH can actually be negative for a very concentrated strong base. And therefore pH is going to be 14 minus this negative answer. So it's actually going to be 14 point, and technically I should keep my 3 digits here, 176. 14.176. Very high pH, meaning it's extremely, extremely basic. So that's the worksheet. These are your calculations you should be expected to do for the test.